100 kilometers above your head, there is a line. It has a name, the Kármán line, and it is the official boundary of space, the altitude above which a flight counts as spaceflight in the record books. An aviation federation drew it in the early 1960s. The engineer it is named after had calculated 84 kilometers, and the committee rounded up because 100 was easier to administer. NASA never agreed and still uses 80, and the atmosphere pays no attention to any of it, thinning out for thousands of kilometers past all three numbers. That line is the only edge of space anyone has ever drawn, and it is made of paperwork. What none of it tells you is which of the three completely different things the word space means is the one you are actually sitting in tonight, or whether any of them is the universe. Because they are not the same thing, and by the end of tonight you will know exactly what the difference is. Get comfortable. Hit subscribe if this is your first time here, because by the end of this, the room you are lying in is going to stop feeling like a place. Now, let's slowly ease into this. Part 1. 3 words wearing one coat. There is a word you have used your entire life without ever once checking what it means, and tonight we are going to check. The word is space. You know what it means. Everybody knows what it means. And that confidence is the problem, because the word is quietly doing at least 3 completely different jobs, and it switches between them in the middle of sentences without telling you. Most of the time this costs you nothing. Occasionally it costs you an entire question. You ask something that feels enormous and profound, and the reason nobody can answer it is not that the answer is hard. It is that the question was assembled out of 2 different meanings of the same word, and it never actually meant anything at all. Let us start with the meaning you probably reach for first. Space, in ordinary conversation, is the place rockets go. It is up there. It begins somewhere above the sky, and once you are in it, you are in space. That version has an official boundary, which surprises most people, and the boundary has a name. It is called the Kármán line, and it sits at 100 kilometers above mean sea level, about 62 miles straight up. Below that line you are flying. Above it you are in space. The organization that draws that line is the Fédération Aéronautique Internationale, which is the body that ratifies aviation and astronautics records, who flew highest, who flew fastest, whether a given flight counts as spaceflight for the purposes of the record book. And here is the first thing worth sitting with. Theodor von Kármán, the Hungarian-American engineer the line is named after, did not calculate 100 kilometers. He calculated something closer to 84. His reasoning was elegant and entirely physical. As you climb, the air thins, and to generate enough lift from that thinning air to hold yourself up, you have to fly faster and faster. At some altitude, the speed you need for aerodynamic lift exceeds the speed you would need simply to orbit. Past that point, wings stop being the thing keeping you up. That crossover, in his numbers, lands around 84 kilometers. The Fédération rounded it to 100 in the early 1960s, not because of new physics, because 100 is a rounder number, easier to remember, easier to administer, and cleaner in a rulebook. And NASA and the United States Air Force never agreed to that number in the first place. For the purposes of awarding astronaut wings, they have long used 80 kilometers, 50 miles. 2 organizations, 2 boundaries, 20 kilometers apart, and no reconciliation between them to this day. Meanwhile, the atmosphere itself pays no attention to either line. It does not stop at 100 kilometers. It does not stop at 80. It thins out gradually and keeps thinning, and the outermost layer, the exosphere, is generally taken to extend to something like 10,000 kilometers. The International Space Station orbits at roughly 400 kilometers, 4 times higher than the official edge of space, and it is still dragging through enough residual atmosphere that it has to be pushed back up, periodically, or it would fall. Astronauts on board are in space by every definition anyone uses, and they are also, unambiguously, still inside Earth's air. So, the first meaning of the word, the one that feels the most concrete and the most obvious, turns out to be a line an aviation federation drew for paperwork. Hold on to that. 100 kilometers up. We are going to come back to it much later, and when we do it, is going to mean something considerably stranger than it means right now. The second meaning of the word has nothing to do with altitude at all. When you ask whether there is enough space between the table and the wall to fit a chair, you are using space to mean extent, the arrangement in which things have positions and distances from each other, and directions. That kind of space is in your kitchen. It is inside your chest cavity. It is between two atoms in a crystal. It is between the Milky Way and Andromeda. It is the same concept at every scale, and it has no boundary at 100 kilometres or anywhere else, because it is not a region. It is a relationship. It is the answer to how far and which way. The third meaning is the one that causes almost all of the damage. In casual speech, and in a great deal of science writing, space gets used as a loose synonym for the universe, for everything. Space is expanding. What is at the edge of space? How much of space is empty? Notice what has happened in those sentences. The word has slid from meaning a region above your head to meaning extent in general, to meaning the totality of existence, and nobody flagged the transition, least of all the person speaking. That slide is where the fake mysteries come from. Consider 4 questions that almost everyone has asked at some point, usually at night, usually around the age of 11, and that continue to circulate on the internet, essentially forever. What is the universe expanding into? What is beyond the edge of the universe? Where, exactly, did the Big Bang happen? And how can the universe be 13.8 billion years old and 93 billion light years across at the same time? Every one of those 4 questions is built on a single assumption, and the assumption is so deeply installed that it does not feel like an assumption at all. It feels like the floor. The assumption is that space is a container, and the universe is what is inside it. That there is an arena, and there are contents, and the contents sit in the arena, the way a coin sits in a jar. The jar would still be a jar if you took the coin out. The arena would still be there if you removed everything from it. That picture is the one you have been carrying since you were old enough to have a picture at all. Modern physics says that relationship runs the other way, not slightly the other way, not with caveats entirely the other way. And it has been saying so, with mounting confidence and increasingly direct experimental support for more than 100 years. Space is not the jar. Space is closer to being one of the coins. It is a thing the universe has, not a place the universe is in. By the end of tonight, you are going to know exactly what the difference is, stated as plainly as it can be stated. I am not going to give it to you yet, because the plain version only lands once you have felt the ground go out from under the alternative. So instead we are going to do this the slow way. We are going to find out who invented the container in the first place, and when, and why he needed it. We are going to meet the man who pointed out, within 30 years, that the container could not possibly be real, and could not get anyone to listen for 2 centuries. We are going to watch a physicist lose 2 years of his life to a single, stubborn assumption about what a point in space is. And then we are going to look at the instruments, the gyroscopes, and the mirrors, and the 4-kilometre vacuum tubes that have measured space doing things a container has no business doing. And at the end of all of that, when the answer finally arrives, there is a strange twist waiting in the last stretch, because a serious fraction of working physicists now suspect that the correction we spend tonight building is itself too generous. That space is not merely inside the universe rather than around it. That space may not be a fundamental ingredient of the universe at all. Get comfortable. We are going to begin where the whole confusion begins. In a room in England in the 1680s, with a bucket of water and a piece of twisted cord, and a man who is about to invent the idea that has been sitting in the back of your head ever since. Part 2. The man who built the container. The container you are carrying around in your head has an author, and his name is Isaac Newton. That is worth saying slowly, because it is easy to assume that the picture of space as an empty arena is simply what space is, that it is not a theory anybody proposed. It is just the obvious description of the obvious situation. It is not. It is a specific claim, made in a specific book, published in 1687, and it was written down deliberately, because Newton knew he was making a claim, and knew it needed defending. The book is the Philosophia Naturalis, Principia, Mathematica, and the passage is in a section called the Scholium. To the definitions, a short discussion Newton placed after his opening definitions and before the laws of motion, essentially to explain what his terms meant. In it, he distinguishes absolute space from relative space, and he writes that absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Read that clause again, with the emphasis where he wanted it. Without relation to anything external. Space, in Newton's system, does not depend on what is in it. It does not depend on anything. It is simply there, unchanging, everywhere, and it would remain exactly as it is if every particle in creation were removed tomorrow. He said the same thing about time in the same passage. Absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external. Two invisible, immovable, indifferent backdrops, one spatial, one temporal, against which everything happens, and neither of which anything can affect. Now, Newton was not being careless. He needed this, and it is worth understanding why, because the need is real, and it does not go away when you remove absolute space. His first law says that a body continues in a state of rest or of uniform motion in a straight line unless a force acts on it. That law only means something if you can say what counts as uniform motion. Uniform relative to what? If all motion is relative, if the only fact available is that this object is moving relative to that one, then the question of which body is really accelerating has no answer, and the first law has nothing to hold on to. Newton needed a standard of rest that was not any particular object. He needed a background. So he wrote one. And then he did something that separates him from almost everyone who had made metaphysical claims about space before him. He tried to show it had consequences you could see. Picture a wooden pail hanging from a cord. Not a modern bucket, a heavy thing with iron bands, half full of water, still enough that the surface is a flat disc. Someone has taken the cord and twisted it, turn after turn after turn, until it is wound tight and straining against itself. And now they are holding the pail steady with one hand and about to let go. They let go. The cord unwinds, and the pail begins to spin. Fast, faster. And the water does nothing. The surface stays flat, exactly as flat as it was, because the water has not been told, yet the wooden walls are turning against it. But water is slippery, and it takes a while for friction to get a grip. So for these first seconds you are looking at a spinning bucket full of still water, maximum motion between the two, and a flat surface. Then the water begins to catch. You can see it start at the walls and work inward, the whole body of it taking up the turn, and as it does, the surface changes. The middle sinks, the edges climb. Within half a minute, you are looking at a smooth, curved bowl of water, riding high against the wooden sides, and the pail and the water are now turning together at the same rate. Reach in, and the water does not slide past your fingers. There is no motion between them at all, and the surface is still curved. Stay in that moment, because it is the whole argument. When the water and the bucket were moving relative to each other, the surface was flat. Now that they are at rest relative to each other, the surface is bent. Whatever is causing that bend, it is not the bucket. So what is the water rotating with respect to? Newton's answer was absolute space. The water is turning relative to space itself, and space is pushing back. And that curved surface on a Tuesday afternoon in a room in England is your evidence that the arena exists. He offered a second version of the argument, cleaner and colder, for anyone who wanted to argue that the room and the earth and the distant stars were doing the work. Imagine two spheres connected by a cord, alone in an otherwise empty universe. Nothing else exists, no stars, no walls, no floor. Now suppose the cord is under tension. The only thing that could put it under tension is the pair rotating, the spheres straining outward against their tether. But rotating relative to what? There is nothing else. If tension in the cord is a real, measurable fact in a universe containing only two spheres and a string, then rotation is real in a universe with nothing to rotate against, and the only candidate left standing is space itself. That argument is genuinely good. It is not a piece of 17th century mysticism you can wave away with a modern textbook. It held the field for 200 years, and the reason it held is that it correctly identifies something that needs explaining. Acceleration does have consequences that velocity does not. You cannot feel constant speed, but you can absolutely feel a turn. Something out there is keeping score. Newton himself was not entirely comfortable with what he had built, and there are hints of that discomfort scattered through his other writing. In the queries appended to the Optics, he goes further than physics strictly requires and connects absolute space to the divine, describing it in terms that suggest space is something like the sensorium of God, the medium through which an omnipresent being is present everywhere at once. That was not a throwaway line. It was his way of answering the obvious objection that an invisible, undetectable, unaffectable arena is a strange thing to insist on. If it is God's presence, it does not need to be detectable. There is also a quiet irony in the structure of the book itself. Newton laid down rules of reasoning in the Principia, and one of them amounts to an instruction not to multiply causes beyond what the phenomena require. An invisible arena that cannot be seen, cannot be touched, cannot be moved, cannot be affected by anything, and shows itself only through the indirect fingerprint of acceleration, is precisely the sort of entity that rule was designed to exclude. Contemporaries noticed. George Berkeley wrote a short treatise called De Motu in 1721, arguing that rotation could be defined perfectly well against the fixed stars, with no need for a container at all. Christian Huygens had already worked out a relational account of rotation in manuscripts he never published. The objection was in the air almost immediately, and it never went away. And notice, please, what has just happened to the two words we started with. In Newton's picture, space and the universe are cleanly, obviously different things, and the difference goes the way your intuition says it should. Space is the eternal stage. The universe is the play. The stage was there before the curtain went up, and would be there if every actor walked off. This is the container, in its original and most confident form, written by the most successful physicist who had ever lived, in the book that would define science for the next 2 centuries. It took under 30 years for someone to point out that it could not possibly be true, and the objection was not experimental, and it was not mathematical. It was a single question, phrased so simply that a child could ask it, and nobody on Newton's side of the argument was ever able to give a straight answer. Part 3. The objection nobody could answer. Move everything 10 meters to the left. Not part of it, all of it. Every star, every planet, every grain of dust, every particle in your body, the whole contents of creation, shifted 10 meters in the same direction at the same instant, with every distance between every pair of things left exactly as it was. Now tell me what changed. That question is the whole of the argument, and it was put to Newton's camp in 1715 by Gottfried Wilhelm Leibniz, who was one of the very few people alive capable of arguing with Newton on equal footing. The exchange ran through the winter of 1715 and into 1716, conducted through a series of letters between Leibniz and Samuel Clarke, an English clergyman and philosopher who was writing on Newton's behalf, and, by most accounts, with Newton reading over his shoulder and supplying material. It is one of the sharpest arguments in the history of the subject, and it ended only because Leibniz died in November of 1716 with his final reply unanswered. Leibniz's position was simple to state and very hard to dislodge. Space, he said, is not a substance. It is an order of coexistences, the arrangement of things with respect to each other and nothing more. Time, correspondingly, is an order of successions. Neither of them is a thing in its own right. They are ways of describing relationships among things that do exist. Take away all the things, and you have not left behind an empty container. You have left behind nothing, because there was never a container to begin with. And then he made the argument that Clarke could not answer. If absolute space is real, Leibniz said, then the arrangement I just described, everything shifted 10 meters east, or rotated, or moved 1,000 kilometers in any direction you like, is a genuinely different state of the world, a different placement in the container. And yet there is no observation, no experiment, no measurement of any kind, in principle or in practice, that could tell the two apart. Every distance is the same. Every angle is the same. Every physical process unfolds identically. Nothing you could ever measure would differ by so much as a decimal place. He then applied two principles he had spent his life developing. The first is the principle of sufficient reason. Nothing happens without a reason why it is so and not otherwise. If the two placements are indistinguishable, there could have been no reason to choose one over the other, and so the choice cannot be a real feature of the world. The second is the identity of indiscernibles. If two supposed states have no discernible difference whatsoever, they are not two states. They are one state, described twice. Absolute space, in Leibniz's hands, does not describe reality. It manufactures distinctions that carry no difference, and then asks you to believe in them. Clarke's replies are worth taking seriously, because he did not simply bluster. He conceded the empirical point. Yes, the shift would be undetectable, and insisted that undetectable and unreal are not the same thing. God, he argued, could have placed the world differently, and that this choice leaves no trace does not mean no choice was made. And then he went where Newton's side always went when pressed. He pointed at the bucket. Position may be undetectable, he said, but acceleration is not. Rotation shows itself. The water climbs the wall. If space were nothing at all, there would be nothing there for the water to be rotating with respect to, and yet the surface bends. Something is real. So the argument reached a stalemate that lasted the better part of 2 centuries. One side had an unanswerable objection about position. The other side had an unanswerable phenomenon about rotation. And no experiment anybody could think of would break the tie, because both sides agreed on every number that could actually be measured. The tie was finally attacked, not broken, in 1883, by an Austrian physicist named Ernst Mach in a book called Die Mechanik, in Ihre Entwicklung, the Science of Mechanics. Mach went straight for the bucket, and his move was to notice something everyone had been ignoring for 200 years. Newton's thought experiment quietly assumes you can strip away the rest of the universe and leave the bucket behaving exactly as it does. But you cannot run that experiment. Every bucket ever spun has been spun inside a universe absolutely stuffed with matter, and the water in it is not merely rotating relative to the pail. It is rotating relative to the Earth and the Sun and the entire population of the fixed stars. Mach's claim was that the stars are doing the work. The curvature of that water surface is a consequence of the water's rotation relative to the total distribution of matter in the universe. And to speak instead of rotation relative to empty space is to speak of rotation relative to nothing whatsoever, which is not an explanation but a refusal to give one. Take away the stars, Mach argued, and you do not get Newton's clean laboratory with absolute space still quietly keeping score. You get a situation in which the words have stopped meaning anything. That idea that local inertia, the resistance you feel when you accelerate, is somehow determined by all the distant matter in the universe became known as Mach's principle. It was never written down as an equation. Mach never gave it a precise formulation, and nobody since has managed to state a version that is both sharp and true. But it did something more important than being correct. It got into the head of a young patent clerk in Bern, who later said it was one of the ideas that pushed him toward general relativity and who gave it the name it still carries. Einstein wrote an admiring obituary for Mach when Mach died in 1916 and credited him openly. He also, over the following decades, quietly walked most of it back, because once general relativity was fully worked out, it became clear that the theory does not actually implement Mach's principle. You can write down solutions of Einstein's equations describing a completely empty universe that still has perfectly good inertial structure, which is precisely what Mach said should be impossible. And in 1949, Kurt Gödel constructed a solution in which the entire matter content of the universe rotating relative to what, if the matter is all there is. The principle turned out to be a brilliant piece of intuition that pointed at the right destination and then failed to survive the arrival. What did survive is Leibniz's argument, and it survived in a way he could not have predicted. That move, noticing that two mathematical descriptions differ in a way nothing physical could ever register, and concluding they must therefore describe one situation rather than two, is now completely standard practice in theoretical physics. It is the reasoning behind gauge symmetry in every modern field theory. It is why physicists say that configurations related by a gauge transformation are the same state rather than two states. And it is going to come back in about 20 minutes in a much sharper form when Einstein runs directly into a version of the shift argument he cannot dismiss inside his own equations, and it stops him cold for 2 years. Here is what I want you to take out of these 200 years of argument. Nobody won. There was no decisive experiment, no crushing measurement, no moment where one side conceded. What happened instead is that somebody eventually built a theory in which the question stopped being askable, a theory where space is not an arena the universe sits in, and is not merely a bookkeeping convenience either, but is something considerably stranger than both camps had imagined. And the first move in that theory was not about space at all, it was about the word now. Part 4. There is no such thing as space now. Say the word space out loud and notice what your mind does with it. Almost certainly, it produces a picture of everything, everywhere, right now, all the stars as they currently are. The room you are in, and the street outside, and the far side of the planet, and the Andromeda galaxy, all of it held together in a single instant, a single three-dimensional snapshot of the universe at this moment. That picture is what people mean by space when they are not thinking about it. It is a slice. It is everything, cut at now. In 1905, Albert Einstein published a paper on the electrodynamics of moving bodies, and one of its consequences is that the slice does not exist. I want to be careful here, because this is the point where people either nod along without absorbing it or dismiss it as wordplay, and it is neither. The result is called the relativity of simultaneity, and the content of it is this: two observers moving relative to each other will not agree about which distant events are happening at the same time. Not because their clocks are badly synchronized, and not because signals take time to travel and they have failed to correct for it. They correct for all of that, perfectly, using the best possible procedure, and they still disagree. One of them says, these two events on opposite sides of the room happened together. The other says, one came first. Both are right. There is no third observer, no privileged referee, no fact of the matter hiding behind the disagreement. Now follow that through to what it does to the word space. If space means everything as it is at this instant, and if which events count as this instant depends on how you happen to be moving, then space is not one object that everybody shares. It is a cut you make, and the angle of the cut depends on you. Let me make that concrete. Imagine reality as a solid block, not a metaphor for the moment, a genuine solid, four-dimensional, with 3 directions of space and 1 of time, containing every event that has ever happened or will happen, sitting there, the way a loaf of bread sits on a board. Every moment of your life is somewhere in it. So is every moment of everyone else's. Take a knife, cut straight down, perpendicular to the long axis, and lift the slice away. What you are holding is an instant, a complete, 3-dimensional map of everything, everywhere, at one moment. That slice is what you meant by space when you said the word. Your kitchen is in it. So is the surface of the sun as it is right now, and a particular star in Andromeda as it is right now, and everything in between. Now let someone walk past you at a steady pace, not fast, just walking, and let them cut the same loaf. Their knife goes in at a very slightly different angle, not because they are careless, because the angle of the cut is set by the state of motion of whoever is doing the cutting, and they are moving relative to you. Their slice comes out containing a slightly different set of events than yours. Something you called simultaneous with this sentence, they call already past. Something you called still to come, they have already put in their slice. Set the 2 slices side by side on the table. Both are complete. Both contain a full, 3-dimensional universe. Neither is defective. Neither is an approximation of the other. And there is no procedure, none, in principle, for determining which one is the real space. 2 people in the same room, one of them walking, holding 2 different universes at an instant, and both of them correct. That is what special relativity does to the container. It does not say the container is empty or full or expanding. It says there is no unique container, because the very act of picking out an instant of saying everywhere now requires a choice that reality does not make for you. Hermann Minkowski, who had been one of Einstein's mathematics teachers in Zurich and who had reportedly considered him a lazy student, saw the geometric structure underneath this before Einstein did. On the 21st of September, 1908, Minkowski stood up at the 80th Assembly of German Natural Scientists and Physicians in Cologne and opened his address with a line that has been quoted ever since. From this hour on, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Read that as a technical statement rather than a flourish, because that is how he meant it. Space by itself is a shadow. Time by itself is a shadow. Neither is the substantial thing. What is substantial, what every observer agrees on, regardless of how they are moving, is the four-dimensional structure and the separations measured within it. Two observers will disagree about how far apart two events are in space. They will disagree about how far apart they are in time. They will agree exactly and always on a particular combination of the two, called the interval. That combination is the invariant. That is what is really there. There is one more piece of structure worth naming, because it is the thing that keeps this from collapsing into pure relativism. Every event in that four-dimensional block has a cone attached to it, a light cone, opening forward into the events it can possibly influence and backward into the events that could possibly have influenced it, with the walls of the cone traced out by light. Every observer, no matter how they are moving, agrees on those cones. They disagree about which events are simultaneous. They never disagree about which events can reach which. So the block is not shapeless. It has a rigid causal skeleton that everybody shares, and the slicing into instants is the soft, observer-dependent part laid over the top of it. Hold that thought as well, because in the final stretch of tonight there is a research program that takes the causal skeleton as the only real thing and rebuilds every distance and every duration out of nothing but that ordering. And the shadows are not nothing. You can absolutely work with a shadow, and physicists do, all day long. But a shadow depends on where the light is coming from, and the space you experience depends on how you are moving. It is a projection of something more fundamental. It is not the thing itself. Notice too how thoroughly this dismantles the argument we just spent 200 years watching. Newton's absolute space was supposed to be the one true arena, the same for everyone, God's fixed backdrop. Leibniz denied it was a thing at all. Neither of them imagined the actual answer, which is that space is real enough to measure and yet is not a single shared object, that you and I, sitting in the same room, are slicing the same four-dimensional reality into different stacks of three-dimensional spaces, and the difference between our stacks is too small to notice only because we are moving slowly relative to each other. Speed up the relative motion and the difference stops being small. At any appreciable fraction of light speed, the slices tilt significantly. Events that one observer places in the same instant get spread across a substantial stretch of the other's time. The disagreement is not a rounding error in the equations. It is the normal condition, and our agreement here on Earth is the special case, produced entirely by the fact that everything we deal with is crawling. And there is a consequence here that people tend to skate past, so let me put it flatly. When you say the universe right now, you are not describing the universe. You are describing a slice you have chosen. If you want to know what a galaxy 10 billion light-years away is doing at this moment, there is no fact waiting to be looked up, because at this moment is your construction, and someone drifting past you at walking pace would build a different one and be equally entitled to it. The phrase feels like it refers to something. It refers to a choice. Notice, also, that this is not a limitation on what we can find out. It would be much less unsettling if it were. If the problem were that light takes time to arrive, and so we always see the past, that would be an inconvenience about information. The fact would exist, we simply could not access it yet. That is not the situation. The situation is that the fact does not exist. Reality does not maintain a list of what is happening everywhere at once, waiting for someone fast enough to read it. There is no such list, and every attempt to construct one produces a different answer depending on who is holding the pen. So here is where we stand, roughly a quarter of the way in. The word space, in its everyday sense, everything, right now, refers to something that different observers construct differently, and that reality does not single out. That is already awkward for the container picture. A container that has a different shape depending on who is looking at it is a strange sort of container. But special relativity is only the demolition. It clears the ground. It tells you what space is not, and it leaves you with a flat, featureless, four-dimensional block that still, in its own way, behaves like a stage that gets sliced at different angles by different people, but a stage that nothing on it can affect. Einstein spent the next 10 years destroying that too, and when he was finished, space had stopped being scenery and had become one of the actors with mass, in a sense, and energy, and the ability to push back. Part 5. The stage stands up and starts acting. In 1907, sitting at his desk in the patent office in Bern, Einstein had a thought that he later called the happiest of his life. The thought was this: a person falling freely does not feel their own weight. Step off a roof, and, for the duration of the fall, gravity vanishes from your experience. Not reduced, not compensated for, gone. You float. Anything you release floats beside you. Every experiment you could perform in that falling box gives the same answer it would give in empty space, far from any star. And the reverse holds too. Seal someone in a windowless room and accelerate it upward, and they will feel a perfectly convincing gravitational field, indistinguishable from standing on a planet. If gravity can be created and destroyed by changing your state of motion, then gravity is not a force in the ordinary sense. Forces do not switch off when you jump. What gravity must be instead is something about the geometry of the paths available about what counts as going straight. That thought took Einstein 8 years and a considerable amount of mathematics he had to be taught by friends, and it arrived in its finished form in a paper called Die Grundlage der allgemeinen Relativitätstheorie, the foundation of the general theory of relativity, published in Annalen der Physik in 1916, running from page 769 to page 822. Here is what that paper does to space. In special relativity, the four-dimensional block was flat and rigid, like a sheet of plate glass. Everything happened in it, nothing happened to it. General relativity replaces that rigid sheet with a field, an actual physical field, on the same footing as the electromagnetic field, with its own equations of motion, its own energy, its own ability to change over time and to carry disturbances from one place to another. Physicists call it the metric field. Its job is to answer the questions how far and how long. Give it two nearby events, and it tells you the separation between them. That is all a metric does, and it is everything, because how far and how long is the entire content of the word geometry. And crucially, this field is not fixed in advance. It is determined by what is in it. The field equations Einstein wrote down have curvature on one side and matter and energy on the other, joined by an equal sign, which means the geometry and the contents are not two independent things. You cannot specify the contents and then ask what the geometry is doing, because the contents are shaping the geometry while the geometry is steering the contents. John Wheeler compressed the whole arrangement into 11 words that have never been improved on. Space-time tells matter how to move. Matter tells space-time how to curve. Stop and look at what has happened to Newton's arena. It is not the arena anymore. It is on the field. It has properties. It has dynamics. It responds to what is in it, and it acts back. It can be curved, and it can be twisted, and, as we will see shortly, it can be made to ring like a struck bell. A container does none of those things. A container is defined precisely by its refusal to participate. But the deepest part of this, the part that actually settles the question we have been circling all night, is not the field equations. It is an argument Einstein made against himself, and it nearly destroyed the theory. Between 1913 and 1915, Einstein convinced himself that the general theory could not be right. He had wanted his equations to be generally covariant, meaning they would take the same form no matter what coordinate system you used, because he saw no reason the laws of physics should care how you label points. Then he found what looked like a fatal problem, and it is called the hole argument. Picture a region of spacetime containing no matter at all, a hole in the distribution of stuff. Outside the hole, everything is specified, all the matter, all the fields, the whole history. Now, Einstein reasoned, if the equations really are generally covariant, then inside that hole, I can take the entire gravitational field and smoothly slide it around, push it a little this way, stretch it a little that way, as long as everything matches up smoothly at the boundary. And the resulting field will also solve the equations. So I have two different solutions that agree completely outside the hole and disagree inside it, which means the matter outside does not determine what happens inside, which means the theory does not predict the future, which means it is useless. He believed that for 2 years, 2 years of a life, during which almost every other year produced something the rest of us are still teaching. He abandoned general covariance because of it, published equations he knew were uglier than they should be, and only returned to the right ones in November of 1915, weeks before completing the theory. The resolution is one of the most quietly radical statements in physics, and it is exactly Leibniz's shift argument, come back with teeth. The two solutions are not two different physical situations. They are one physical situation, described twice, and the reason is that the points inside the hole do not have identities of their own. There is no such thing as this particular point of space, considered independently of the field defined there. When you slide the field over, you are not moving the field to a different set of pre-existing locations. There are no pre-existing locations. The locations are made of the field. Asking whether the field is here or slightly over there is asking a question that has no referent, in exactly the way Leibniz said, asking whether the universe is 10 meters to the left has no referent. I want you to sit with that for a moment, because it is the hinge of the entire evening, and it is the single hardest thing here to actually believe, rather than merely accept. The assumption Einstein was stuck on, the one that cost him 2 years, is the assumption you are holding right now. It is the assumption that a point in space is a place, that before anything is there, before any matter arrives, before any field is defined, there is a here and a there and a somewhere else, an infinite scaffolding of empty positions waiting to be occupied. That is what everybody thinks. It took the most capable physicist of the 20th century 2 years to stop thinking it, and he only stopped because his own equations backed him into a corner and would not let him out. There is no scaffolding. Position is not something the universe supplies in advance and then fills. Position is a relationship among things that exist, and where there is nothing, there is not empty space, there is nothing, including no space. Einstein knew exactly how large this was, and he said so, repeatedly, in language much plainer than the mathematics. In the note, he appended to the 15th edition of his popular book on relativity, published in 1952, 3 years before he died, he wrote a sentence I want you to carry with you for the rest of tonight. Space-time, he wrote, does not claim existence on its own, but only as a structural quality of the field. Space does not claim existence on its own, and in the same passage, even more bluntly, there is no such thing as an empty space, that is, a space without field. Not empty space is rare, or empty space is hard to make. There is no such thing. Where there is no field, there is no space, because space was never anything other than a description of what the field is doing. Now, in fairness, Einstein was not consistent on this over the decades, and the honest version of the story includes his wobbles. In an address in Leiden in 1920, he argued the opposite-sounding point that general relativity ascribes real physical qualities to space and therefore restores a kind of ether, a medium, though one with no substance and no state of motion and no rest frame you could measure yourself against. That is not a contradiction so much as an emphasis. He is insisting that space is not nothing. It has properties, it carries energy, it does things. What it does not have is independent existence. There was also a technical objection raised by Erich Kretschmann in 1917 that sharpened everyone's understanding. Kretschmann pointed out that general covariance by itself has no physical content, because you can rewrite almost any theory in generally covariant form if you are willing to work hard enough. The substantive property, the one that actually distinguishes general relativity from everything before it, is background independence, the fact that there is no fixed structure sitting underneath, no stage that was there before the play started. Newton's theory has a background. Special relativity has a background. General relativity has none, and that absence is what makes it the first physical theory in which space is not presupposed. So, by 1916, on paper, the container is gone. Space is a field. The field is part of the contents of the universe, and where there is no field, there is nothing at all. On paper, that is the caveat that matters, and it is the one an honest skeptic should press on, because everything I have described so far is a chain of arguments about what has to be true if certain equations are true. It is beautiful, and beauty is not evidence. So let us go and look at what the instruments say, because in the century since, we have built machines that measure the geometry of space directly, machines that watch it being twisted by a spinning planet, and machines that catch it ringing after two black holes collide. And what those machines report is not a philosophical position, it is a number with error bars. Part 6. The instruments agree. A container cannot be dragged around by what is inside it. That is more or less the definition of a container. So, if you want to know whether space is scenery or a participant, you do not need a philosopher. You need a gyroscope and a very good telescope, and you need to point them at a spinning planet and watch what happens. That experiment ran for 16 months, from 2004 to 2005, aboard a satellite called Gravity Probe B, and the analysis of its data took another 6 years. The instrument was 4 gyroscopes, each a sphere of fused quartz coated in niobium, about the size of a ping-pong ball, and at the time they were manufactured, they were the most perfectly round objects ever made by human beings, deviating from a perfect sphere by roughly 40 atomic layers. They were cooled to near absolute zero, spun up, and set floating in a polar orbit around the Earth, with a telescope on board locked onto a single guide star, so the spin axes had something absolutely fixed to be compared against. The prediction was that the axes would drift. Not because of any force acting on them, they were in freefall, shielded, isolated to a degree that took decades to engineer, but because the geometry they were moving through is not flat, and a gyroscope carried through curved geometry comes back pointing somewhere else. That is the geodetic effect, and it is the larger of the two. General relativity predicted a drift of 6,606.1 milliarcseconds per year. A milliarcsecond is 1/360th of 1,000th of 1 degree. The measurement came back at 6,601.8, plus or minus 18.3. The second effect is the interesting one for us. The Earth is not merely sitting in space, it is rotating. And general relativity says a rotating mass does not simply curve the geometry around it, it twists it, dragging the surrounding structure around with it, like a spoon turning in honey. The name for this is frame dragging, and the prediction for a gyroscope in that orbit was a drift of 39.2 milliarcseconds per year, in a direction perpendicular to the geodetic drift. The measured value, published in Physical Review Letters on the 31st of May, 2011, was 37.2, plus or minus 7.2. That is a 19% uncertainty on a small effect, and I am not going to oversell it. It is a confirmation, not a precision test, and the team spent years of post-flight analysis fighting an unexpected problem with electrostatic patches on the gyroscope surfaces that nearly sank the whole result. Independent measurements, using laser, ranging to the Legios and LAIRS satellites, have since found the same thing by a completely different route. It is worth saying that frame dragging was not a modern surprise. Joseph Lense and Hans Thöring derived it from Einstein's equations in 1918, 3 years after general relativity was completed, and at the time it looked like a partial vindication of Mach. Rotating matter really does drag the local standard of non-rotation around with it, just nowhere near completely. It took 93 years and a satellite to see it. But hold the number up against the picture we started with. The Earth's rotation is twisting the geometry around it. The spin of the contents is dragging the arena. Newton's absolute space remains always similar and immovable, without relation to anything external. The gyroscopes say otherwise, in milliarc seconds per year. And then there is the measurement that ends the argument entirely. It is the 14th of September, 2015, and the detector outside Livingston, Louisiana, is running. 2 arms, 4 kilometres each, at right angles, evacuated to about a trillionth of atmospheric pressure, so that not one stray molecule of air can nudge the result. At the end of each arm hangs a mirror weighing 40 kilograms, suspended in a cascade of pendulums to isolate it from every truck on every road within 50 miles. A laser runs down both arms and comes back, and the machine spends its entire existence comparing the 2 lengths against each other. At just before 5 to 10 in the morning, coordinated universal time, the comparison stops matching. One arm gets very slightly longer, while the other gets very slightly shorter, then the other way, then back, faster and faster, over about 0.2 of a second, sweeping upward in frequency and then stopping. 7 milliseconds later, 6.9 to be exact, the detector at Hanford, in Washington State, 3,000 kilometers away, records the same shape. 7 milliseconds is how long it takes something moving at the speed of light to cross the continent between them. Now hold the size of it. The length change in those 4-kilometer arms was about 1 part in 10 to the 21st. In absolute terms, that is roughly 10 to the minus 18 meters, about 1,000th of the width of a single proton, across 4 kilometers. And 2 machines on opposite sides of a country agreed on it, 7 milliseconds apart. What had happened was that 1.3 billion years ago, 2 black holes of about 36 and 29 solar masses had finished spiraling into each other, roughly 410 megaparsecs away, and in the final fraction of a second had converted around 3 solar masses of material entirely into a disturbance in the geometry of spacetime, which then propagated outward at light speed until some of it arrived in Louisiana. Read that sentence again with attention to where the energy went. It did not become light. It did not become particles. It became a wave in the distance relation itself. For that to be possible, the distance relation has to be a thing capable of carrying energy, and the amount of energy involved briefly exceeded the light output of every star in the observable universe combined. And notice what the mirrors did, or rather, did not do. The mirrors did not move through space. Nothing pushed them. What changed was the amount of space between them. That is not a figure of speech, and it is not a simplification for the audience. It is the literal content of the measurement, published in Physical Review Letters on the 11th of February, 2016. The collaboration did not believe it at first, and that reluctance is itself informative. LIGO had a standing practice of secretly injecting fake signals into the data stream to keep the analysts honest, and the first serious hypothesis inside the building was that somebody had done it again. It took weeks of checking to establish that no injection had been made, and months, more of analysis before the statistical significance was pinned down at better than 5 sigma, a false alarm rate of less than 1 event in 200,000 years of observation. The announcement came almost 5 months after the event itself. There is one more thing in that measurement worth pausing on, because it goes past the container question and into something odder. Gravitational waves are not the only thing that can carry energy through a region, but they are the only thing that carries energy by being the region. Light traveling through a vacuum needs somewhere to travel. A gravitational wave is a change in what somewhere means, propagating. The geometry is simultaneously the medium, the message, and the thing doing the moving, and there is no way to draw that picture in which space is a passive backdrop, because in this case, space is the entire event. These are not the only receipts, they are just the loudest. In 1960, Pound and Rebka sent gamma rays up a 22.5-meter tower at Harvard and measured the frequency shift caused by the change in geometry over that height, getting a result within about 10% of prediction. Radar signals grazing past. The sun arrived measurably late compared with a flat geometry calculation, an effect confirmed by the Cassini spacecraft in 2003 to better than 1 part in 10,000. The binary pulsar, discovered by Hulse and Taylor in 1974, has been spiraling inward for half a century at precisely the rate you get if it is losing energy to gravitational waves, agreeing with prediction to better than 0.2%. And starlight bends around the sun by about 1.75 arcseconds at the limb, measured at an eclipse in 1919, which is not light being pulled by a force, but light going straight through geometry that is not flat. So the picture from the instruments is unanimous, and it is quantitative. Space bends, space twists, space stretches and rings, and carries energy across 1 billion light years. Whatever it is not an absence, and it is not a stage, and it is very obviously part of the inventory of the universe, rather than the shelf the inventory sits on. Which means it is time to step back, put the pieces together, and then walk directly into the question that this whole distinction was invented to answer the one you almost certainly asked as a child, and that nobody has ever given you a satisfying answer to. Part 7. The question that eats itself. Let us stop for a moment and put the pieces on the table together, because we have covered a lot of ground, and the next stretch depends on all of it. We started with a word doing 3 jobs, a line 100 kilometres up, drawn for record keeping, a relationship of distance and direction that exists inside your kitchen as much as between galaxies, and a loose synonym for everything. We watched Newton write the container into existence in 1687 because he needed a standard of rest and defend it with a bucket. We watched Leibniz point out, within 30 years, that a container you cannot detect and in which every possible placement of everything is indistinguishable from every other is not a description of the world, but a set of distinctions with no differences. We watched that argument sit unresolved for 2 centuries. Then we watched special relativity remove the shared instant, so that space stopped being one object everybody agreed on and became a slice whose angle depends on how you are moving. Then general relativity turned that slice into a field, something with dynamics, energy, and the capacity to be reshaped by what is in it. Then the instruments confirmed it, in milliarc seconds per year and in fractions of a proton width. So the container is gone. Now watch what happens when you take the most famous question in all of popular cosmology and ask it without the container. The question is, what is the universe expanding into? Almost everyone asks it eventually. It has the feel of a question with a hidden answer, as though physicists know and are not saying, or as though the answer is some higher dimensional hyperspace that would be too complicated to explain on television. Neither is true. The reason you have never been given a satisfying answer is that the question does not have a subject. There is nothing for the phrase into what to refer to. And the reason it feels like it must have one is that you learn the expansion from a diagram, and every diagram ever drawn to explain it has the same fatal feature. Here is what the physics actually says. The standard description of a large-scale universe is a solution to Einstein's equations found by Friedmann, Lemaitre, Robertson, and Walker, and its content is this. Pick out the matter that is at rest with respect to the overall flow, the galaxies, roughly speaking, and give each piece a permanent label. Those labels never change. A galaxy keeps the same label forever. Then there is a single number, called the scale factor, which multiplies every distance between every pair of labels, and that number grows with time. That is the entire mechanism. Nothing travels anywhere. The galaxies keep their labels. What changes is the answer the geometry gives when you ask how far apart 2 labels are. Yesterday, it said 1 number. Today, it says a larger one. The distance relation is doing the changing, and the distance relation is not a thing that has to be situated inside anything else in order to change its value. Compare that with the diagrams. The rubber sheet with weights on it, a 2-dimensional surface, drawn sitting in a 3-dimensional room so that you can see it sagging. The expanding balloon with dots on the skin, a 2-dimensional surface, drawn as the boundary of a 3-dimensional volume of air, which is very obviously the thing it is expanding into. The raisin bread rising in an oven, a three-dimensional loaf in a kitchen with a ceiling above it. Every one of those pictures works by taking a space and embedding it in a larger space so that you can look at it from outside. And every one of those pictures thereby introduces exactly the feature the mathematics does not contain. When a cosmologist tells you to think of galaxies as dots on a balloon, the instruction that actually matters is the one that gets mumbled. You must consider only the surface, not the rubber, not the air inside, not the room the balloon is in. The surface, alone, with nothing on either side of it. And of course you cannot really do that, because you have a balloon in your head, and balloons have insides. The mathematics has no such difficulty, and the reason is a piece of geometry that was worked out 60 years before anybody needed it for gravity. In 1827, Carl Friedrich Gauss proved something he was pleased enough with to name it the remarkable theorem. The curvature of a surface can be determined entirely by measurements made within the surface, by creatures confined to it, with no access to any outside. Draw a triangle, measure its angles, and if they do not add to 180 degrees, you know your world is curved, without ever leaving it. Bernhard Riemann generalized the whole approach in 1854 to any number of dimensions. That is what intrinsic geometry means, and general relativity is written in it from the ground up. Every curvature, every expansion, every twist in Einstein's equations is defined by relations inside the geometry. There is no embedding. There is no outside in the equations, not as an unknown, not as a variable left blank. The concept does not appear. Asking what it expands into is like asking what direction is north of the North Pole. The words are all real words. The question has no referent. The same dissolution happens to the sister question, the one about where the Big Bang took place. People picture a point somewhere out there, a location the explosion happened at, and imagine that, with a good enough telescope and a good enough map, you could find the spot and put a marker in it. But if expansion is the scale factor growing rather than material flying apart, then running the film backwards does not converge on a place. It converges on a time when the scale factor was small, when every label was close to every other label everywhere. The event did not happen somewhere. It happened everywhere, at all the labels at once, including the one you are sitting on. The Big Bang happened in this room, in the sense that this room's worth of labels was part of it, along with every other room. The observations back that up in the simplest possible way. Look at the microwave background, the oldest light there is, released when the universe was about 380,000 years old, and it arrives from every direction at very nearly identical temperature, 2.725 Kelvin, varying from patch to patch by about 1 part in 100,000. There is one larger variation, a lopsidedness of about 3.4 thousandths of a Kelvin, and that one is our own doing. It is the Doppler signature of our motion at roughly 370 kilometres per second relative to the radiation. Subtract that, and the sky is astonishingly even. If there were a centre, and we were off to one side of it, the sky would not look like that. And I want to add the clarification that stops this from being misheard, because it matters. The expansion is not a force stretching everything. Your body is not being pulled apart. The Earth is not drifting away from the Sun. The Milky Way is not growing. Anything held together by gravity or electromagnetism, a galaxy, a star system, a planet, a molecule, simply stays the size it is, because the binding wins and the expansion is not a pressure pushing outward. Expansion is only visible between things far enough apart that nothing is holding them together. It is a statement about the largest scales, and on any scale you can see with your eyes it does exactly nothing. There is one more consequence of separating expansion from motion, and it is the one that makes people certain a rule is being broken. Distant galaxies have recession speeds that grow with distance, and past a certain distance those speeds exceed the speed of light. That sounds like a violation of the most famous limit in physics, and it is not one, because the limit applies to something moving through the geometry past something else nearby. Two objects at opposite ends of an expanding universe are not moving past each other at all. There is no shared frame in which to lay their velocities side by side and compare them. The number you get by multiplying an expansion rate by a distance is not a velocity in the sense the speed limit governs. It is a rate of change of a separation, and nothing forbids it being large. The history here is quieter than it should be. Georges Lemaître, a Belgian priest and physicist, derived an expanding solution and connected it to the observed velocities of galaxies in 1927, publishing in a Belgian journal that essentially nobody outside Belgium read. Edwin Hubble published the empirical distance-velocity relation in the Proceedings of the National Academy of Sciences in 1929 and got the name. Hubble's original number for the expansion rate was about 500 kilometres per second per megaparsec, roughly 7 times too large, because his distance calibration was badly wrong. The relationship was right. The number was not, and getting that number right turns into one of the strangest ongoing problems in physics, which is where we are going next. Because once you accept that the universe is not expanding into anything, a second question arrives immediately, and this one is not malformed. It is perfectly well posed. It has a numerical answer, and there are 2 excellent ways of measuring it that disagree with each other by more than 5 standard deviations. Part 8. A room with no walls and no outside. Every enclosed thing you have ever encountered has an outside. That is not a foolish assumption. It is the most thoroughly evidenced generalization in your entire life. Rooms have corridors beyond them. Houses have streets. Bodies have air around them. Oceans have shores. Planets have sky. Boxes have rooms. And in every single case, without one exception in several decades of continuous observation, being inside something has meant there was something else to be outside of. You did not decide to believe that. It was installed by repetition. So, when someone says the universe has no edge, the sentence does not go in, it bounces. You hear it, you nod, and some part of you keeps quietly asking, what is past the last galaxy? Because the demand for an outside is not stupidity. It is a lifetime of consistent evidence pushing back against a claim that contradicts all of it. Let me try to disarm the demand rather than argue with it. Start with the difference between 2 words that get used as if they mean the same thing: finite and bounded. Something is finite if there is only so much of it. Something is bounded if it has an edge, a place where it stops and something else begins. Almost everything in your experience is both, which is why the 2 feel like one idea. Now take the surface of the Earth. Just the surface, the 2-dimensional skin, ignoring everything above and below it. Its area is finite, about 510 million square kilometres, a number you can write down, and it is completely unbounded. There is no edge. You can walk in any direction for as long as you like, and you will never reach the last piece of ground, never find a fence, never come to a place where the surface stops. You will come back to where you started, which is a very different thing. Nobody finds that paradoxical, and the reason nobody finds it paradoxical is that you can picture the Earth from outside. You can see the sphere sitting in space, and the fact that its surface has no edge is obviously fine, because there is a whole universe surrounding it. The finite and unbounded part is easy, precisely because the outside is doing the work of making it comfortable. Now do the same thing without the outside. That is the actual ask, and it is harder, and I am not going to pretend otherwise. What the mathematics says is that a geometry can be finite and unbounded without being embedded in anything. The unboundedness is not a consequence of curving around inside a larger space. It is a property the geometry has on its own, definable entirely from measurements made inside it, exactly as Gauss showed for surfaces 200 years ago. The picture of the sphere sitting in a room is a crutch, and it is a crutch that costs you the very thing you are trying to understand. And so the question about the edge of the universe turns out to belong in the same bin as the question about what the universe is expanding into. Not unanswered, malformed. An edge is a place where a thing stops and something else takes over. For there to be an edge of everything, there would have to be something on the other side that is not everything, which is a contradiction rather than a mystery. There is no outside, not because it is hidden, not because it is unreachable, not because our instruments are not yet good enough. There is no outside, because outside is a relationship between 2 things, and there is only one thing. And I think the reason that lands as unsatisfying rather than as an answer is that it feels like a trick with language. It is not. Consider how many of your convictions about the world are actually convictions about grammar. Inside implies outside because the word was built that way, by people describing pots and rooms and bodies, none of whom were describing the totality of existence. The word was never tested against a case where there is nothing else. When you apply it there, and it comes back with an absurdity, that is not the universe being evasive. That is a tool being used outside the conditions it was designed for, and reporting a fault. Which brings us back, at last, to that line 100 kilometres above your head. Remember it? The Kármán line, the official boundary of space, set by an aviation federation for the purpose of deciding which flights go in which column of the record book. An engineer calculated 84 kilometres. A committee rounded it to 100 because 100 is easier. And a different organisation, in a different country, uses 80 and has never changed its mind. That is it. That is the complete inventory of edges of space that anyone has ever successfully drawn. Not a wall at the far end of the cosmos, not a shell, not a membrane, not a place where things stop a bookkeeping convention about wings and altitude, agreed by some people and not by others, 62 miles up. When you were a child, lying awake, wondering what was at the edge of space, the honest answer was that the only edge that exists is the one you could reach in about 8.5 minutes on a good rocket, and even that one is made of paperwork. Now, having said all that, I want to be scrupulous about what physics actually knows here, because there is a real measurement involved, and it is more interesting than the confident version. The shape of the universe on the largest scales is described by its curvature, and curvature is something we can measure. The technique is essentially Gauss's triangle, scaled up. Take features in the microwave background, whose true size we can calculate from physics, measure the angle they subtend on the sky, and see whether the answer matches flat geometry. If the geometry were positively curved, the features would look slightly larger than expected. Negatively curved, slightly smaller. The Planck satellite, combined with measurements of the acoustic scale in the distribution of galaxies, gives a curvature parameter of 0.001 plus or minus 0.002. That is consistent with exactly flat. It is the reason you will hear people say the universe is flat. But notice what those error bars permit. Consistent with 0 is not the same as 0. The measurement is compatible with a universe that is very slightly closed, one that does curve around on itself, finite and unbounded like the surface of the Earth, with a curvature radius so enormous that the piece we can see looks flat for the same reason a field looks flat, despite sitting on a sphere. If that is the situation, the universe is finite, and there is still no edge. And flatness, even if it is exact, does not settle whether the universe is finite. This is the part almost nobody mentions. A flat geometry can still close up on itself if its topology is right. Take a flat sheet, join the left edge to the right edge, and the top to the bottom, and you have a torus perfectly flat everywhere, no curvature at any point, finite in extent, and with no edge anywhere. A three-dimensional version of the same trick would give a flat, finite, edgeless universe in which travelling far enough in a straight line brings you home. That would leave a signature. If space closes up on a scale we can see across, then light from the same region could reach us by two different routes, and the microwave background would contain repeated patterns, matched circles of temperature, the same patch of early universe printed on the sky twice, in different places. Cosmologists have searched for those circles since the early 2000s. They have found nothing, which pushes the size of any such repetition out beyond the region we can observe, and settles the question not at all. So the honest position is this: we do not know whether the universe is finite or infinite. We may never know, because no set of observations made inside a horizon can settle what lies outside it. And if inflation happened, it made the situation worse on purpose, because a period of enormous early stretching would have flattened out any curvature and pushed any topological repetition far beyond our reach, explaining why we see flatness while simultaneously destroying the evidence that would tell us what we are actually in. What we do know is that whichever answer is right, there is no wall. Finite or infinite, curved or flat, the universe does not stop at a place, because stopping at a place requires somewhere for the stopping to happen, and there is no such somewhere. Which raises the obvious next question, and it is one we can actually answer with numbers. If there is no edge, why does everyone quote a size? Part 9. The map is not the territory. Everyone quotes a size because there is a real number, and the number is real, and it is not the size of the universe. The figure you have heard is 93 billion light-years across. It gets printed as though it were the dimension of a thing, as though someone laid a measuring tape from one end of creation to the other. It is not that. It is the diameter of a bubble, and the bubble is centered on you. Here is where it comes from. The universe has an age. The best current figure, from the Planck satellite's final analysis of the microwave background, is 13.797 billion years, give or take about 23 million. Light travels at a finite speed. Therefore, at any moment, there is a limit to how far away something can be, and still have had time to send you a signal since the beginning. Anything beyond that limit exists, presumably, and simply has not been able to reach you yet. The boundary is called the particle horizon, and everything inside it is called the observable universe. Now, the naive calculation says that if the universe is 13.8 billion years old, the horizon should be 13.8 billion light-years away, and the whole thing should be about 27.6 billion light-years across. That is the arithmetic that makes people suspicious when they hear 93. It looks like somebody has made an error of a factor of 3.5. Nobody has. The extra factor is expansion, and it is the clearest possible demonstration of why space and the universe cannot be the same thing. Follow one photon. It leaves a patch of hot plasma very early on and starts traveling toward what will eventually become you. It covers ground at exactly the speed of light, the entire way, no cheating, no shortcuts. But while it is in flight, the distance relation between its origin and its destination is growing. Every year, it makes progress. And every year, the ground it has already crossed gets a little longer behind it. And the ground still ahead gets a little longer too. After 13.8 billion years of travel, the photon arrives. And the patch of plasma that emitted it, which has since become galaxies and stars, is now using the distance you would get if you could freeze the expansion and lay out a tape measure about 46.5 billion light-years away. That is not the photon traveling further than light can travel. It is the photon traveling for 13.8 billion years through a geometry whose distances were increasing the whole time. Double the radius, and you get the 93 billion light-year figure. It is a number about what light has had time to do inside an expanding geometry. It is not a wall, it is not an edge, and it is not a property of the universe at all. It is a property of your position in it and how long the universe has been running. Let me take you out there so you can see how ordinary it is. Travel to the particle horizon, 46.5 billion light-years, straight out, in whatever direction you like. You arrive. Look around. There is nothing. Not nothing in the sense of emptiness. There are galaxies, in every direction, roughly as many as there are around home, arranged in the same filaments and sheets and voids. There is nothing in the sense of no event, no wall, no shimmer, no curtain, no thinning, no place where the stars run out and something else begins. It is an unremarkable stretch of universe, with an unremarkable population of galaxies going about their business, and if there were anybody living there, they would have no idea that anything special had been claimed about their neighborhood. Turn around and look back the way you came. Your own galaxy, the Milky Way, is now on the horizon from here. It is at the very limit of what can be seen, sitting at the boundary of somebody else's observable universe, looking exactly as edge of the world as this place looked from home, which is to say, not at all. And there is more universe past you, from here. There always is. Move again, and the horizon moves with you, staying obediently 46.5 billion light-years out in every direction, because it is not a place. It is a relationship between light, time, and wherever you happen to be standing, and it follows you around like the horizon at sea. So the 93 billion light-year figure is the width of a window, not the width of a room. And the room might be very much larger. The The standard inflationary picture suggests it is larger by an enormous factor, though the specific number depends on model assumptions and is not something anyone has measured. It might be infinite. We covered why we cannot tell. There is a second horizon out there, and it is the one that should genuinely unsettle you, because it is not about what we can see, it is about what we can ever reach. The expansion is accelerating. That was established in 1998 by two independent teams working on Type Ia supernovae, and it earned the Nobel Prize in Physics in 2011. Acceleration means that the distance to a given galaxy is not merely growing but growing faster over time, and that produces a limit called the cosmological event horizon, a distance beyond which a signal sent from here today will never, in the entire future of the universe, arrive. Not slowly, never. The current figure sits at roughly 16 billion light-years in the same co-moving units. Compare that with 46.5 and let the ratio land. The great majority of the galaxies you can currently point a telescope at are already permanently beyond contact, not too far to visit too far, for a message sent at light speed to ever catch them. Their light from the past keeps arriving, and will keep arriving, redshifted further and further, so we will go on watching them recede for a very long time. But nothing we do from now on can ever touch them. They have already left. Now hold both horizons next to each other, and notice that neither one is a fact about the universe. Both are facts about the relationship between light, time, and expansion. Both move if you move. Both would be different numbers if the expansion history were different. They are properties of a geometry, and geometry is the thing we established some time ago is inside the universe rather than around it. Which brings us to the crack in the middle of all these numbers, and it is a serious one. Every figure I have quoted tonight, the age, the horizon distance, the curvature, the composition, comes out of fitting a model to data. The single most important number in that fit is the current expansion rate, called the Hubble constant, and there are two independent ways of measuring it. The first works from the early universe. Take the pattern of hot and cold patches in the microwave background, fit the standard cosmological model to it, and read out what the expansion rate must be today. Planck's final answer is 67.4 kilometres per second per megaparsec, plus or minus 0.5. The second works locally and involves no cosmological model at all. Build a distance ladder, variable stars whose brightness reveals their distance, calibrated against geometry, then used to calibrate supernovae. In more distant galaxies, measure how fast those galaxies are receding, and divide. The SH0ES collaboration published their most comprehensive version in 2022 in the astrophysical journal Letters. 73.04, plus or minus 1.04. Those two numbers do not agree. The gap is more than 5 standard deviations, which in this field is the threshold where you stop calling something a fluctuation. And the gap has not closed. As the measurements have improved, both sides have spent 15 years hunting for the mistake, tightening error bars, checking calibrations, rebuilding the ladder rung by rung, and the disagreement has become sharper rather than softer. There is a related, milder disagreement of the same kind, sometimes called the sigma-8 tension, about how clumpy the matter distribution should be. The microwave background predicts one level of clumpiness. Surveys that measure how distant galaxy images are sheared by intervening mass tend to come back slightly smoother. That one is not at 5 sigma and may yet evaporate. But it is the same shape of problem, the early universe fit and the late universe measurement pulling in different directions about how the geometry has behaved over 13 billion years. Nobody knows what it means. It might be an unrecognized, systematic error in one method. It might be new physics in the early universe, some extra ingredient that changes how the microwave background is interpreted. It might be something about dark energy that the standard model does not capture. But notice what the two teams are actually arguing about. They are not arguing about a galaxy, or a star, or a particle. The quantity in dispute is the rate at which the distance relation between things is changing. The most prominent unresolved problem in modern cosmology is a disagreement about a property of space, and that is a useful place to arrive, because we have spent all night establishing that space is not an absence. Now, It is time to look directly at the part of it that is emptiest, the deep vacuum, the regions with no stars, no dust, no atoms, nothing at all, and find out what is actually going on in there. Because it turns out the emptiest place you can construct is not quiet, and the disagreement between what theory predicts it should contain and what we measure it to contain is the largest number in physics. Part 10. The emptiness is the busiest part. Build the emptiest thing you can build. Take a metal box, pump out every molecule of air, cool the walls until the thermal radiation inside is negligible. Shield it from every field you can shield it from. Keep going, ideally in your imagination, until you have removed everything it is possible to remove. What you are left with is what physicists call the vacuum state, and the entire history of the subject can be told as a series of people opening that box and finding it occupied. The reason is that the modern description of the universe is not made of particles. It is made of fields, one for each kind of particle, spread everywhere, and what we call a particle is a localized excitation in one of them, a ripple with a certain minimum size. Remove all the particles, and the fields do not go away. They cannot. What you get is every field sitting in its lowest possible state. And in quantum mechanics, the lowest possible state of an oscillating thing is not zero. It is a residual, irreducible jitter, and it is not optional. It follows directly from the uncertainty relation, because a field that was exactly zero everywhere and exactly still would have both its value and its rate of change pinned down precisely, which is not permitted. So the empty box is full of fields in their ground states, fluctuating, and the question is whether that is a bookkeeping device or a physical fact you can measure. In 1948, a Dutch physicist named Hendrik Casimir proposed a way to check. Put two flat, uncharged metal plates in a vacuum, very close together and parallel. Because the plates are conductors, they impose conditions on the electromagnetic field between them. Only certain wavelengths fit in the gap, the way only certain notes fit on a guitar string of a given length. Outside the plates, every wavelength is allowed. So there are more modes fluctuating outside than inside, and the imbalance should push the plates together. It was an audacious prediction, because the force is tiny and falls off extremely fast with separation. It took decades to test properly. In 1997, Steve Lamoureux published a measurement in Physical Review Letters using a torsion pendulum to detect the attraction across separations from about 0.6 of a micrometer out to 6 micrometers, and found agreement with theory at roughly the 5% level. The following year, Mohideen and Roy pushed the precision to about 1% using an atomic force microscope. The plates move. The effect is real. I want to be honest about the interpretation, because this experiment gets overclaimed constantly. You will frequently hear the Casimir effect described as a direct measurement of the energy of empty space. It can be calculated that way, and the calculation works, but it can also be derived without ever mentioning zero-point energy at all, as a relativistic version of the ordinary forces between fluctuating charges in the two slabs of metal. Both routes give the same answer. So the Casimir effect is very good evidence that quantum field theory is right about the vacuum, and it is not proof of one particular story about what the vacuum is made of. That distinction matters, and most popular accounts drop it. The evidence does not rest on Casimir alone. In 1947, Willis Lamb and Robert Rutherford measured two energy levels in hydrogen that the best theory of the day said should be exactly equal, and found them differing by about 1058 megahertz. The gap is caused by the electron interacting with the fluctuating electromagnetic field of the vacuum being jostled, essentially, by nothing. That measurement is one of the founding results of quantum electrodynamics, and the theory that explains it now agrees with experiment to a dozen decimal places in some quantities. There is also vacuum polarization, worked out by Ewing and Serber in 1935. Put an electric charge in empty space, and the vacuum around it does not stay in different transient particle and antiparticle pairs, flicker in and out, orienting themselves, partially screening the charge. This means that the strength you measure for the electromagnetic interaction depends on how close you get, and it genuinely changes as you probe harder. We have talked about that number before on this channel, and I will not rehearse it, except to note the shape of the result. The emptiness around a charge behaves like a material with a dielectric response, and the response is measurable. And here is the one that ought to reframe your sense of what you are made of. Roughly 99% of the mass of a proton is not the mass of the quarks inside it. The quarks contribute a tiny fraction. Almost all of the rest is the energy of the gluon field binding them and the structure of the strong force vacuum in which they sit. Which means that when you stand on a scale, almost all of what the scale is reporting is the energy of fields in what would otherwise be called empty space, packed into regions the size of a proton. You are, by mass, mostly the properties of the vacuum. Two more results are worth naming quickly because they show the vacuum can be pushed rather than merely observed. Julian Schwinger calculated in 1951 that a sufficiently strong electric field would stop merely polarizing the vacuum and start tearing real particle pairs out of it permanently. The threshold is around 1.3 times 10 to the 18th volts per meter, which no laboratory on Earth has yet reached, though the most powerful lasers are creeping toward it. And, in 2011, a team using a superconducting circuit demonstrated the dynamical Casimir effect. Move a mirror fast enough and it radiates real photons, generated out of the vacuum by the motion itself. Now, for the number that makes physicists uncomfortable. If the vacuum has energy, that energy should gravitate. General relativity does not care what kind of energy you hand it. Energy curves, geometry, full stop. So we can ask what quantum field theory predicts the vacuum energy density to be, and then go and measure what the universe's actual expansion behavior implies it to be, and compare. The comparison is the worst in the history of science. Depending on where you cut off the calculation, the theoretical estimate exceeds the observed value by something in the region of 120 orders of magnitude. That is not a factor of 120. It is a 1 followed by 120 zeros. If the theoretical figure were right, the universe would have blown itself apart before atoms could form. Something is cancelling it to 120 decimal places, and nobody can say what or why. It is called the cosmological constant problem, and the honest position after 50 years of work is that we do not have a solution, only a collection of proposals that do not quite work. What we do have is the measured value, and it is not zero. The universe's expansion is accelerating, which requires something with negative pressure spread evenly through the geometry, and the current accounting puts it at roughly 68% of everything. Dark matter, whatever it turns out to be, is about 27. Ordinary matter, every atom, every star, every planet, everything anyone has ever touched, is about 5. Read that budget again, with tonight's question in mind. The dominant component of the universe, by a wide margin, is a property of empty space. There is one final twist in this part, and it is the strangest thing in it. In 1976, William Unruh showed that whether the vacuum contains particles depends on who is asking. An observer moving at constant velocity through empty space sees a vacuum. An observer accelerating through the same region sees a warm bath of particles at a temperature proportional to their acceleration. Both descriptions are correct. There is no fact about how many particles are in the box that is independent of the observer's state of motion. The effect is real in the theory and vanishingly small in practice. The temperature works out to something like 4 times 10 to the minus 21 Kelvin for every meter per second squared of acceleration, which is why nobody has detected it directly. But the principle is the same one that produces Hawking radiation at a black hole horizon, and it is not in doubt among people who work on this. So put the whole part together. The emptiest region you can construct contains fields that cannot be switched off, whose fluctuations push metal plates around, shift the energy levels of hydrogen, screen electric charges, supply almost all of your body weight, dominate the energy budget of the universe, and disagree with theory by the largest margin in the history of physics. And even the question of how much is in there does not have an observer-independent answer. That is not an absence. That is the busiest part of the inventory, which sets up the last move of the night, and it is the one that takes everything we have built and turns it over. Because we have spent 2 hours demoting space from container to contents, from the shelf to the item on the shelf. And there is a serious body of current research arguing that even that is too generous. That space is not an item at all. That it is something the items are doing. Part 11. What if space is the output? Start with a bookkeeping question that turns out to be the crack in everything. How much can fit in a region of space? Not how much matter, how much information, how many distinct states could that region be in? For anything you have ever dealt with, the answer scales with volume. Double the linear size of a hard drive and you get 8 times the capacity, because you have 8 times the room to put things in. Capacity goes as length cubed. That is so obvious, it barely qualifies as a claim. In the early 1970s, Jacob Bekenstein was worrying about black holes and the second law of thermodynamics. Drop a hot cup of tea into a black hole and its entropy appears to vanish from the universe, which would let you break the second law whenever you liked. Bekenstein argued that black holes must therefore carry entropy themselves, and that the entropy must go up when you feed them. Stephen Hawking, who initially disagreed, then proved him right in a stronger form by showing black holes radiate and have a genuine temperature. The formula they arrived at is one of the most consequential in physics, and its content, stripped of the constants, is this: the entropy of a black hole is proportional to the area of its horizon, measured in Planck units, divided by 4. The area, not the volume. Sit with how strange that is. Entropy is a count of possible states. If you want to know the maximum amount of information that can be packed into a region of space, black hole thermodynamics says the answer scales with the surface bounding it, not with the interior. Double the radius and the capacity goes up by 4, not 8. And this is not a statement about black holes specifically, it is a bound. Try to cram more information than that into any region and it collapses into a black hole, and you are back at the area limit. Something is wrong with the picture of space as a 3-dimensional thing with independent stuff going on at every point. If it were, capacity would scale with volume. It does not. Gerard Hooft took that seriously in 1993 in a paper called Dimensional Reduction in Quantum Gravity, and argued the natural reading, the true degrees of freedom of a gravitating region, are not distributed through its interior at all. They can be described as living on a 2-dimensional surface around it. Leonard Susskind sharpened it a year later in a paper he titled The World as a Hologram. The 3-dimensional world we experience is an image of data stored on a 2-dimensional projection at roughly 1 degree of freedom per Planck area. For 4 years, this was a suggestive argument with no concrete example. Then, in November of 1997, Juan Maldacena wrote down one. His result is technical, and the short version is this. Take a particular kind of curved 5-dimensional spacetime called anti-de Sitter space with gravity in it. Now take a completely different theory, a quantum field theory with no gravity at all, living on the 4-dimensional boundary of that space. Maldacena's claim, which has survived nearly 30 years of checking, is that these are not 2 theories that resemble each other. They are the same theory, written twice. Every question you can ask in one has an exact translation in the other. The physics is identical. Now hold the shapes side by side. One description has 5 dimensions and gravity. The other has 4 and none. One of the spatial directions, the one running from the boundary inward, simply does not exist in the second description. It is not hidden there. It is not curled up small. It is not approximated. It is absent, and yet the 2 theories agree on everything. So where does that direction come from? In the boundary description, motion along it corresponds not to going anywhere, but to changing scale, to asking about the theory's behavior at coarser or finer resolution. A spatial dimension in one description is an organizing principle about resolution in the other. That is not a metaphor about how it might work. That is the dictionary. The next step tied it directly to something you can name, In 2006, Shinsei Ryu and Tadashi Takayanagi found the rule connecting the two sides. Pick a patch of the boundary and ask how entangled it is with the rest, how much quantum correlation exists across the divide. The answer, they showed, equals the area of a particular minimal surface reaching into the interior. Geometry on one side is entanglement on the other. Areas in the bulk are literally computing entanglement, entropies on the boundary. And then, in 2010, Mark van Ramsdonk read the relation backwards and asked the question that gives this part its name. If area equals entanglement, then what happens to the geometry if you reduce the entanglement? Let me put you inside the answer rather than describing it. Picture two regions of space, side by side, perfectly ordinary, a meter apart, say. The distance between them is real, measurable, uncontroversial. Now imagine a dial, and what the dial controls is the amount of quantum entanglement between the degrees of freedom describing the first region and those describing the second. Turn it down, gently. The regions move apart. Not because anything pushed them, nothing moved. No force was applied. No energy was expended pushing masses around. The distance between them simply increased because the distance was a measure of how correlated they were, and you have made them less correlated. Keep turning. The gap widens. The bridge of space, connecting the two regions, grows longer and begins to narrow, stretching like something being drawn out, thinning in the middle. Keep going. The connection pinches down to a thread, and then to nothing at all, and the two regions come apart, and here is the part to hold, because it is not what you expect. They do not end up as two places with a very large gap between them. They end up as two spaces with no spatial relationship to each other whatsoever. There is no distance between them anymore, not an infinite distance. No distance, because distance was the entanglement, and you have removed it. Van Ramsdonk's conclusion was that the connectivity of space-time, the plain fact that the room you are in hangs together, that here and there are related at all, is built out of quantum entanglement between its parts. 3 years later, Maldacena and Susskind pushed it into a slogan, an Einstein-Rosen bridge, a wormhole joining two regions, and an Einstein-Podolsky-Rosen pair, two entangled particles, may be the same thing described two ways. Geometric connection and quantum correlation, one phenomenon. This is not the only route to the same destination, which is part of why people take it seriously. Loop quantum gravity comes at the problem from the opposite end, quantizing geometry directly rather than deriving it, and finds that area and volume become quantized observables with discrete spectra and a smallest, non-zero value, at the Planck scale, an area of order 10 to the minus 70 square meters. In that framework, the fundamental object is not a continuum at all, but a graph, a network of nodes carrying volume and links carrying area, and smooth space is what that network looks like from very far away. Causal set theory strips things further still. Assume only the causal ordering of events, that skeleton of light cones we met earlier, plus a rule for counting, and a theorem from 1987 shows the entire geometry can be recovered from that ordering alone. Distance is not assumed, it is reconstructed. These programs disagree with one another about nearly everything. They do not agree on the mathematics, the methods, or which questions matter. They agree on one structural feature, and it is the one that concerns us tonight. In every case, space is an output. The fundamental description does not contain it. You put in something else, entanglement structure, a spin network, a causal order, and space comes out the far end as a description of the result at large scales. And there is a matching result on the other half of the pair, which I will mention only briefly because it deserves its own night. When you take general relativity and quantize it by the standard procedure, the equation you get for the state of the universe has no time variable in it, none. The most natural reading is that time, like space, is not fundamental, that what we experience as duration is a relationship between one part of the system and another part acting as a clock. A tabletop version of that idea was demonstrated with a pair of entangled photons in 2013. So, the space and time split you have taken for granted your whole life may be doubly derived. Now the caveats. Because they are substantial, and this field is regularly oversold. Anti-de Sitter space, where the holographic dictionary is best understood, is not the universe we live in. It has negative curvature and a boundary you can hang a theory on. Our universe appears to have a small, positive vacuum energy and no such boundary, and constructing a version of the correspondence that applies to it is an unsolved problem that many capable people have failed at. Nobody has derived the space in this room from anything. What has been shown is that in certain, carefully constructed model universes, space provably emerges from something else, and that is a very different claim from having proved it about ours. Nor is discreteness a free lunch. If space were a fine grid, very high-energy photons traveling for billions of years might arrive fractionally out of step with lower-energy ones. Gamma-ray burst observations have looked for exactly that, and the arrival times are clean enough to rule out the simplest versions of pixelated space, in some cases past the Planck scale itself. But notice where this leaves Einstein's sentence, the one from 1952 that I asked you to carry. Space-time does not claim existence on its own, but only as a structural quality of the field. When he wrote it, he meant something precise and, by the standards of tonight, almost conservative, that geometry is what the gravitational field is doing and cannot be peeled away from it. Half a century later, people are using the same sentence to mean something he never proposed and might not have accepted. That geometry is what entanglement is doing, that the field itself is the approximation, which means we have arrived, finally, at the answer I have been holding back all night. Part 12. The answer, plainly. Here is the difference, stated as plainly as it can be stated. The universe is the totality, all of it, every particle, every field, every photon in flight, the geometric relations between all of them, the entire history that connects them, and the laws that history obeys. Nothing is left out, because the word means everything there is. Space is one structural property of that totality. It is the answer the universe gives when you ask how far apart two things are and in which direction. It is a relation among the content's dynamic, capable of curving and twisting and stretching, carrying energy, full of activity, even where it is emptiest, and sliced out of four-dimensional reality at an angle that depends on who is doing the slicing. It is one item in the inventory rather than the room the inventory is kept in. So the universe is not in space. Space is in the universe. That is why space and the universe are not the same thing, and the difference is not a technicality about definitions. It is the difference between an ingredient and the whole dish, and every question that treats them as interchangeable comes out malformed. Go back to the picture you walked in with, the jar and the coin, the universe as a container and everything else rattling around inside it, a jar that would still be a jar if you tipped out every coin, an arena that would still be there if you removed the play. There is no jar. There never was. What you have been calling the jar is one of the coins, and the shape you thought was the container is a relationship that the contents have with each other. Take away everything, and you do not get an empty container. You get nothing, and nothing does not have dimensions. Which means the sentence you have half believed your whole life, that you are somewhere, in a place, that would still be there, if you were not, is not quite right. You are not in the universe the way a coin sits in a jar. You are part of what the universe is doing. The distance from your hand to the far wall is not the room you happen to be sitting in. It is a relation you are participating in, one that involves you and the wall and everything between, and it would not exist as it is if you and the wall did not. And the three jobs the word was doing at the start of the night can now be separated cleanly, which is worth doing because you will hear all three used interchangeably again tomorrow. The first was outer space, a region above a chosen altitude, which is a fact about atmospheric density and about paperwork and about nothing else. The second was geometric extent, how far, which way, which is a genuine physical structure present in your kitchen exactly as much as it is between galaxies, and it is the one physics has spent 400 years learning to describe. The third was space, as a synonym for everything, and that one is simply an error. It is the only one of the three that causes trouble, and it causes all of it, because it takes an ingredient and quietly promotes it to the whole. Notice, too, that the correction runs in the direction nobody expects. When people are told they have misunderstood something about space, they generally brace for the universe getting larger for another zero on the end of a number, another layer of scale to feel small against. This is the opposite. The universe did not get bigger tonight. A word got smaller. Space turned out to be one feature of reality among others rather than the setting reality takes place in, and that demotion is what makes the questions answerable. You lose the container, and you gain the ability to ask a coherent question about the totality. Now go back through the questions we started with, and notice that they have all quietly resolved themselves. What is the universe expanding into? Nothing, and the question has no subject. Expansion is a number multiplying the distances between things, and a distance relation does not need to be situated inside a larger space in order to change its value. The only reason the question feels compulsory is that every diagram you have ever seen drew a surface inside a room. What is beyond the edge of the universe? Nothing, and there is no edge, because an edge is where one thing stops and another begins, and there is nothing else for it to begin. Finite or infinite, curved or flat, and we genuinely do not know which there is no wall. The only edge of space anybody has ever managed to draw is 100 kilometres above your head, and it is a line an aviation federation chose because it rounded nicely that a different agency in a different country never agreed to, and that the atmosphere itself sails straight through without noticing. Where did the Big Bang happen? Everywhere, including exactly where you are, not at a location in a pre-existing space, because there was no pre-existing space for it to happen at a location in. And how can the universe be 13.8 billion years old and 93 billion light-years across? Easily, because that figure is not the size of the universe. It is the width of the window, your position, and the age of the universe allow you to see through, and it will be a different number tomorrow, and a different number for anyone standing anywhere else. 4 questions that have kept people awake, and not one of them was a question about the universe. All 4 were questions about a container that does not exist. I said at the start that there was a twist waiting at the end, and it is this. Everything I have just told you, the whole careful demotion of space, from arena to ingredient, may still be too generous, because the count of what a region can hold scales with its surface rather than its interior, which it should not if space were really 3-dimensional, all the way down. Because, in the model universes where the mathematics can actually be done, a spatial dimension turns out to be a way of talking about something else entirely, and can be translated away without loss. Because if you take 2 neighboring regions and reduce the entanglement between them, the space between them stretches, thins, and ceases to exist. Because quantize the geometry directly, and you get a graph, not a continuum. Because strip everything away except which events can influence which, and the distances come back on their own without being put in. Einstein wrote, 3 years before he died, that space-time does not claim existence on its own, but only as a structural quality of the field. He meant something specific and, by tonight's standards, almost cautious, that geometry is what the gravitational field is doing, and you cannot separate the two. He did not mean what the holographers mean. He did not live to see people take the same sentence and push it a level deeper, until the field itself is the approximation and the structure underneath is made of correlations. Which leaves us here, at the end, with the honest position that space is inside the universe rather than around it is settled. It has been settled since 1915, and the instruments confirmed it decades ago, in milliarc seconds per year, and in fractions of a proton width. What is not settled, what nobody can currently answer, is whether space is a fundamental part of the inventory or something the rest of the inventory produces. If it turns out to be the second, then the room you are lying in tonight is not a place the universe occupies. It is a shape the universe is currently making. The walls are still there. The distance from your bed to the door is still exactly what it was. Nothing about the evening has changed. But the arrangement itself, the plain, unremarkable fact that things are located anywhere at all, would be a pattern rather than a container, an output of something more basic that has no notion of near or far. And you would be part of the pattern, not situated in it, participating in it, along with the wall and the window and the light coming in from a star whose photons have been traveling through a distance relation that has been quietly lengthening beneath them the entire way. The universe is everything. Space is one of the things it does. Whether it is one of the things it is made of is a question for another night, and nobody, at the moment, can tell you the answer.